I start?
Yes.
Okay, thank you. So, hello everyone to the second session of this workshop on gravitational waves. So, in the first session, we have seen that gravitational waves are perturbations on the metric field, tensor perturbations on the metric field that propagates according to a wave equation. We have seen that in general, it's very hard to compute the solutions. However, in vacuum, we are left with plane waves. And usually we resort to gauge fixing in order to get further simplified equations and to get the real degrees of freedom correctly identified. We have also seen that in the presence of matter, we can resort to the so-called green functions method, so to get solutions for the wave equation, and even though we can further simplify using some useful approximations as far we are very far from the source. Okay. So in this second session, we shall resort to a different approach to the analysis of gravitational waves in general relativity or in any gravity theory, okay? So today we will start with the so-called Newman-Penrose Formalism, or it is also known as the spin coefficient formalism. Okay, and the origin of this formalism is due to the problems of general relativity when we introduce matter with spin, namely, for instance, fermionic fields. As in bosonics, it works pretty well. So usually when we introduce semi-integer spins, namely for fermions, we have some problems. Namely, we need to introduce a further formalism called the spin connection one. Or we can resort to a different approach to general relativity, which is the tetrad formalism. Okay, so the fundamental pieces are no longer the metric field, but rather vector fields on the tangent bundle. Or we can also rewrite this formalism in terms of two component spinors. We shall use throughout this presentation the formulation given by vector fields on the bundle, okay, on the tangent bundle. So furthermore, I would like to note that we cannot convert the tetrad and metric formalism when we have fermions, although for bosons we can do that. Okay, so the idea is to start with a system of n independent vector fields, these ones here, and their dual one forms, such that they are can be inverted. Remember that the metric field can be written in this form, or resorting to these vector fields, we can write the metric field in this form. And these two components, if you adopt a matrix representation, that means that in a matrix, the components of those that matrix can be given by the old one in the space-time coordinates by this transformation. So in 4 dimensions, let us choose these vectors, et, ex, ei, y, and ez. So we are fine with this definition, but Newman and Penrose explored even further, and they introduced for the tetrad by 4 vectors, 2 being real and 2 being complex conjugates of each other, namely k, l, m, and m bar. I would like to draw your attention that sometimes in the literature it is usually called n and l, okay, instead of kl. So the Newman-Penrose tetrads obeys these orthogonality conditions, such that they are mainly based on the light construction. And in particular, this condition here occurs for a metric with a signature minus plus plus plus. If we had the other signature, that will be minus plus here and the minus here, or alternatively, the one would become minus one. All the other things would hold. Okay, so moreover, we can look into the Riemann tensor. Remember that one of the most fundamental descriptions of curvature is given by the Riemann tensor, and we can decompose it into its irreducible parts, namely a viral tensor with 10 components, a traceless Ricci tensor with 9 components, and a scalar curvature. In fact, this is the Newman-Penrose Formalism, which was adapted for instance, gravitational waves by Early et al. So for a nearly plane wave, and making use of the properties of the Riemann tensor, the properties of the symmetries of the Riemann tensor, these components over here can be reduced into 6 independent components. Okay, these on the right side of this slide, we can see the Newman-Penrose quantities and the Newman-Penrose Ricci components. Usually we call these psi's. The decomposition of the viral tensor has Newman-Penrose quantities, but we can also have the decomposition of the Ricci and the scalar curvature. So we will adopt the convention of all of these quantities are the Newman-Penrose quantities. So by the results of Early et al., they found that from those 6 independent components, the non-vanishing and linear independent ones are psi2, which corresponds to a longitudinal mode, the real and imaginary parts of psi3, which accounts for a mixed vectorial x and y modes, and the psi4, which denotes the 2 transverse tensor polarizations, plus and cross, as we have seen for general relativity. Moreover, there is also a further scalar mode, namely the transverse scalar breathing mode. We will see really soon the brief picture of these polarization modes when we have a gravitational wave propagating along the z direction. So, as I said it, these are 6 independent components. However, there are further ones that are non-zero, but are related to these ones. So these are the linearly independent and non-vanishing quantities. So, as I said it, so let's picture a collection of point particles that are that live in a plane orthogonal to the direction of propagation of the gravitational wave, and let's see what happens when a gravitational wave passes through that collection of point particles. So these red polarizations, I think you should be more familiar now, as we have seen in the linear formalism of general relativity. This is the so-called cross, the plus, sorry, and cross polarizations. So you remember that this circle is being stretched and compressed in opposite directions. So I also mentioned that they are 2 further in any metric theory by the results of Early et al. 2 further scalar modes. A breathing one, you see here, so it compresses in all directions. It's a concentric circle, okay? It comes in and out. As for the longitudinal one, this longitudinal one, as you can see here, is in the z direction. So it compresses and stretches along the direction of the propagation of the gravitational wave. As for the vector ones, look into here, it's like a cross polarization, but it's no longer living in the plane that is orthogonal to the propagation of the gravitational wave, but rather it compresses and stretches particles, the collection of particles along the propagation of the gravitational wave. So these here arise from the psi3 component. The longitudinal one arises from the psi2, and phi22 is the breathing mode, which leads to a breathing mode, and the psi4 gives the usual polarization in general relativity. So this formalism is quite useful in order to address gravitational waves in any metric theory. We can analyze, for instance, Browns decay. So if we add an extra field to Einstein's equations or whatsoever, we can analyze what happens for on the gravitational wave solutions. Okay, so this is highly motivated from group theory, in particular the so-called E2 group, which is the group of the Lorentz, which is the group of Lorentz transformations for massless particles, can be used to classify these 4 NP variables based on their transformation properties. Only psi2 is invariant, and the amplitudes of the 4 NP variables are not observer independent according to these transformations. You see, only psi2 is invariant, but the other ones can be measured differently by different observers. However, one of them is, for instance, is 0. They are 0 for every observer. Okay, let's suppose it gives a function of z or something, but for an observer, and it gives 3/4 of that function for another observer. But if one is 0, that one is measured being 0 for any observer. So, and as it was observed by Alves et al., the name of each class is composed of the Petrov type and of its non-vanishing Weyl tensor, and the maximum number of non-vanishing amplitudes, here these 4 NP quantities, which and the dimension of the representation, as seen by any observer. Both the Petrov type and the dimension of representations are independent of the observer. Of course, we are considering, for simplicity, that the wave is propagating along the z direction, and we are looking at the same frequency for any monochromatic wave. Okay, so this is a way to classify gravitational waves. In mathematical sense, we can picture this in a decreasing generality over here. So these classes 2, 6, 3, 5, etc., according to the vanishing or non-vanishing of these Newman-Penrose quantities, not only have a physical meaning, namely it can be observer independent or not, like this, but it can also allow us to really classify a gravity theory. Okay, it will be more these are more abstract ways of classifying, but we will see these in detail or for specific cases in order to get some insight on what I mean by this classification. Okay, and of course this classification by Early was based on the Petrov-Pereny classification, which is a more general one. Okay, and this general classification is for any theory, not for gravitational waves. For gravitational waves, for anything. Okay, so it's according to the existence of which of those Newman-Penrose vectors are null. Okay, so by looking into that, this gives very interesting properties, and we can have some physical meaning. I'm not going to give any much further insight on this because it gives a lot. It would be a second class of not gravitational waves, but classification of gravity theories, because this classification also holds for black holes, for instance. Okay, so it gives a lot of interesting properties. We introduce further quantities related to optical scalars, etc., which gives some geometrical insight of the theory. So this Petrov and Pirani also, because they derived independently, is a wonderful scheme to address gravity theories. Okay, so in particular, we have seen the linear polarization of gravitational linear formalism of general relativity, and according to the Newman-Penrose formalism, we only have psi4 being non-vanishing and independent, so that we only have the cross and plus polarization modes. But in particular, we can address other gravity theories and look into the gravitational wave solution of such theories. And why do we need to seek beyond general relativity? This is what you should be asking right now. So, despite its well-known successes of general relativity, for instance, at solar system level, or the prediction of black hole, prediction of the observation recently of a black hole shadow, and even the prediction of gravitational waves, or even the common use of GPS, the global position system, general relativity has some serious problems that need to be solved. In particular, it is not fully consistent with the quantum mechanics or the quantum field theory. Hence, we do not have a fully consistent quantum gravity theory. It presents singularities, for instance, black holes, or even the origin of space-time, the Big Bang. We also have, at late times, the problems of dark matter and dark energy, and the so-called cosmological constant. So, you can see perhaps general relativity is a little bit rusty, like this old train. So we need to look for alternative solutions. You know, general relativity can really have a crack in it, okay? As Newton's law, Newton's gravity, was reformulated by Einstein, and in a different, more general way, with completely different meaning for gravity, okay? And on the right side of this slide, I would like to draw your attention for a general scheme of some physical areas. Namely, we have the missing of a fully quantum gravity. Okay, this is a huge problem. In particular, this problem is important for what we are considering here. We have seen that the excitation or perturbation of the metric field in tensor way, right? The tensor perturbation is propagates has a wave. It's a gravitational wave. But if we had a quantum picture, this propagation would be a particle, the so-called graviton. Okay, but addressing a classical field, the perturbation of a classical field, and trying to understand the quantum meaning of it are completely different things. Okay, so these gravitational waves are really gravitons or not? We have missing pieces so to understand this issue. Okay. The other problem that we had on general relativity, or at least with its compatibility with observations, is namely the dark universe. So in order to account for the astrophysical and the cosmological observations, we need to introduce two major components in the universe, namely dark matter and dark energy. So you see, the matter that we know only accounts for around 5% of the total energy content of the universe. That means that we need to introduce roughly 95-96% of unknown. Okay? And are these components particles? Are they fluids, or are they some kind of sort of dark gravity? So, and to better understand this picture, I would like to give you an historical view. So, for instance, the planet Uranus was found by Herschel in 1781. And several observations of that planet showed that its trajectory does not follow perfectly the Newton's predictions. So it was strange. And in particular, some years later actually, Adams proposed the existence of an exoplanet which might affect the Uranus trajectory. So, and at the same, and independently, Leverrier also proposed this kind of approach. So, a new planet would be the cause of this, the difference between what we observe in the trajectory of Uranus and what would be expected. So this is the introduction of a new dark component, in the sense that we are introducing a component that we do not really understand what it is. It could be so in this analogy, it would be which kind of planet is it? A terrestrial one, a gaseous one? What kind of planet? Right? We didn't know. In particular, they didn't know. And at the same time, at the same year that Leverrier proposed also this hypothesis, Gale and the rest found Neptune incredibly close to Leverrier calculations. So theoretical calculations really allowed to the discovery of a real component. So it's no longer a dark component because it was identified as the planet Neptune. On the other way, let's look into a different approach. So Leverrier proposed a new planet, since it was so successful in explaining the Uranus trajectory, in order to now explain Mercury's ones, which was in contradiction with Newton's gravity. So, you know, there were a lot of false news. So fake news are not actually new things. It also happened in the past. So about the discovery of a supposed volcano planet. However, improved calculations required at least 2 new planets to account for the observations. So oppositely to Leverrier proposal, not only we had to introduce 1, but we need to introduce 2. You see the thing? An analogy to dark energy and the dark matter, right? In order to account for observations, we needed to introduce 2 dark components. So these kind of proposals failed, okay? But Einstein really solved the problem with general relativity. So this kind of, you can see like a modified gravity in comparison with Newton's law. So it was actually not the presence of further planets, further dark components, but rather a modification of gravity theory. We can also think that general relativity suffers from the same problems. So we can look into alternative theories of gravity. So we can change gravity, Einstein's gravity, but not by introducing some scalar field, right, a dark component, but we can say that look, or at least look into different ways that gravity gravitates, in the sense that we can add more gravity, less gravity. We can add different couplings to matter fields, for instance. Could these different approaches solve the problems that we know? So it's one open question in today's research. And one of the simplest, or perhaps really the simplest generalization of Einstein theory, at least in vacuum, is f(r) theories. So we look into the Einstein-Hilbert action and we replace the Ricci scalar by a generic function of it. So it could be r plus r squared. It could be r plus 1 over r, for instance. It could be different things. So in general, it would be f(r) theories. So if we now vary the action relativity to the metric, we get some modified Einstein field equations, right? Which are more complicated as we introduced higher derivatives in the metric fields, okay? This notation of primes, these primes are derivatives with respect to the scalar field, to the, the scalar curvature, or Ricci scalar. So we will now look into gravitational waves of f(r) theories, since these are one of the simplest generalizations of general relativity. And we will look into mainly into the work of Alves et al., published in 2009. Let us choose f(r) to be r minus alpha r to the power of minus beta. So in this formulation, what we are looking into is that, well, we have general relativity, and we are now slightly modifying with an extra term, or an extra curvature term. You see, beta does not need to be positive. It can be positive or negative. And so it can increase the curvature at late times or decrease it, depending on the value of the exponent. So the field equations over here can be recast as it is for this specific choice of f(r) theories. You see, it's even though really hard to solve. It's not easy as it was in general relativity. It has many more terms. The trace of the field equations can be also computed, right? We take the trace of this equation and we get this. Remember that in general relativity, the Ricci scalar was equals to 0 in vacuum, or minus t, the trace of the energy momentum tensor in the presence of matter fields. So we see here that higher derivatives contribute to the scalar curvature solution, as well as this modification relatively to the Einstein term. Okay. And remember, we are specializing the form of f(r) theories in order to address gravitational waves. However, a more general approach can be performed, namely introducing a scalar field which is related to the, in this case, to the derivative of this f(r) function. Okay, and we will see it. Or we can, for instance, try to separate things and say that the action functional is r plus f(r), in the sense that we are really looking into in what ways, which new physics, the inclusion of this extra term, more curvature or less curvature, will be different from general relativity. Okay? So let's do a simple exercise step by step. So what about alpha equals to 0? Let's look into here. Alpha equals to 0 means general relativity. Remember, we have not really, I have not shown how to address general relativity for the Newman-Penrose formalism. Let's do this, since general relativities can be seen as a particular solution of f(r) theories. remember that these are the non-vanishing and linearly independent Newman-Penrose quantities. We need to understand that there are other properties, other symmetries of the Ricci tensor and the Ricci scalar. So let us look into these properties, okay, or symmetries. So let's try to understand how to analyze gravitational wave solutions in the Newman-Penrose formalism. So in vacuum, we all agree that in vacuum it will be r equals to 0, and consequently the Ricci tensor is also vanishes, which could also be seen from these modified field theory, modified field equations, as we set alphas to 0, right? So remember, these are the symmetries here and the linear independent and non-vanishing Newman-Penrose quantities. From the properties, remember, if r equals to 0, let's look into here. So r equals to 0, that means that RLK is 0 and RLK is also 0, right? So let's look into psi2. Psi2 is RLK. So if R, the Ricci scalar is 0, also the psi2 is 0. Okay, this is 0, and I've told you, as I told you, if it's 0 for an observer, it's 0 for any observer. So the issue comes how to compute the other quantities in general, or these quantities, because we are using LK, this notation of the Newman-Penrose tetrad. Remember that it was introduced in these slides. Okay, in these slides. So the Ricci tensor written in any vector of these bases is actually the Ricci tensor in the space-time coordinates, and each element of these bases has the index correspondent, the corresponding index. Okay, you see, RAB is actually R mu nu, A mu, B nu. Okay, this is how to compute or to look into these quantities here. And for instance, if we are working in space-time coordinates, we can relate immediately these quantities written in the Newman-Penrose basis to the space-time basis. Okay, so RLK is equals to RMN. Remember, okay. These are all 0. It can be you see, now you can expand R. It will be R mu nu mu nu, L mu K nu, L mu K nu, right? Computing these quantities are vanishing, and so are these Newman-Penrose quantities. However, we have no further constraints on the form of RL m bar, L m bar. Therefore, the only non-vanishing NP quantity is psi4. Since psi4 is a complex quantity, okay, remember, these are scalars, these are real components, real quantities, and these are complex quantities. So psi4 is complex, therefore two polarization modes exist, and psi4 represents the tensor 1, so it's the plus and cross polarization. So general relativity, as we have seen from the linear formalism. An additional note, you remember that this class that I told you of N2, so only psi4 is non-vanishing. We can look back into this classification, okay, and we see that this is precisely that general relativity lies in the class N2, meaning that it's observer independent, okay? So all the Newman-Penrose quantities are vanishing except for psi4. Okay, this is the usefulness of a classification system. You see, with this simple example, it's not simple to be seen in the at first time, okay? But by looking into it again and again, as you can see, and you can check it by yourselves later on or after this workshop, you can look and see clearly the usefulness of such classification system. So let's do another example, okay? Let's choose beta equals to -2, meaning that we are choosing a function which is roughly r minus alpha r squared. This is the so-called Starobinsky model. It's a quite successful model for inflation, okay? The early time acceleration of the universe after the Big Bang. Okay, so this is the system of classification of theories, as we have seen. These are the Newman-Penrose quantities that are important for non-vanishing and linear independent for the classification of gravitational waves. And these are the properties of the Ricci and tensor and the Ricci scalar. Okay, so what do? We look, for instance, to the trace of the field equation here, okay? And we have a kind of wave equation with the mass term for the Ricci scalar. Can you understand what I mean? So we have a wave equation for the Ricci scalar with the, let's say, m squared, like this, okay? With solutions are plane wave, and we can actually find the constraint from the k wave number. Okay, so let me before moving forward, let's see. When I am looking into the trace of the field equations, and what we find is actually a modification of the scalar field, we clearly are in the presence, with the mass term here, we are clearly in the presence of further polarization modes. Let's check which modes could appear. So in the limit of small curvatures, so really far from the source, the Einstein field equations modified in the so-called FoF theories can be solved. These metric field equations can be solved, and the non-vanishing components of the Ricci tensor are like these. Look at that; these are expressed in terms of the Ricci scalar. So we can compute, we can look into it, and we can do the exercise, expanding RL, L, and so on. So these quantities here, such that we find that the non-vanishing quantity is psi3. Okay? Is the vanishing, sorry. This is the vanishing one. We have a psi2, a psi4, and the I22. Let me give you a physical insight on this. That means that we do not have, at least here, at least in this example, we do not have vector polarizations, but we have a tensor one, which we would expect, but we also have two scalar modes. In particular, we can understand that scalar mode comes precisely from the mass term, from the existence of a mass term in the trace of the field equations. Usually, this gives rise to a scalar mode, scalar polarization. Okay, and the classification of Newman-Penrose, we can look, right? Only psi3 is 0. The other ones are non-vanishing. So we are in the more general case, which is I2, which are I6, sorry, where all these 6 polarization can appear for some specific Lorentz observer. but the amplitude psi2 is observer independent. Okay? So, as I told you, we can address the FoF theories and the gravitational wave solutions in such theories in a more general way by introducing a scalar field. Let's do it. So the idea is to identify the derivative with respect to the scalar curvature of FoF with a scalar field, and to define an effective potential, so that the field equations can be cast in this form. You see the usefulness of using this. So we have here the so-called Einstein Tensor. So we have the usual left-hand side of the Einstein field equations, but we have now a kind of modification, or non-trivial, because it's 1 over phi, sorry, here. So we need to understand in what sense these extra dynamics, right? It's a dynamics of a scalar field, introduce extraporization modes in comparison to general relativity counterpart. So we impose f2 primes to be non-zero, and that's f prime to be invertible. So the first condition arises from the so-called Dolgov-Kawasaki instability, so that we cannot have instabilities in the Ricci scalar. And the second one, it's obvious, we need to, this is a mathematical tool, a mathematical approach. So we need to invert to get the solution, right, for FoF. So we need to be invertible. So we can, firstly, let us linearize these field equations. So we expand around the Minkowski space-time, and we also expand the scalar field, okay, around a constant background value. Okay, by doing that, we end up with this linearized version of the field equations. Okay, we have also expanded the effective potential accordingly. So we assume that it's usually a kind of harmonic potential, such that we can really approximate this in a more stable. We are looking for stability in these extra terms relatively to Einstein theory. Okay, and this HF is a quantity that was introduced. So it's the excitation of the scalar field with respect to the background value. So remember that in general relativity we use the trace reverse quantity of H, right? I'm not saying that this is the trace reverse, rather this is the inversion of the trace reverse, so that we get the solution for the metric field. So the solution for the metric field are the trace reverse quantities like this. These would be the regular terms from general relativity, but as we have seen from here, we have a further mode, a scalar mode actually. It will be a breathing scalar mode. And we can include here, or equivalently, we have included the scalar contribution in the trace reverse quantity. Remember that it's just to take the trace reverse over everything here. So that in vacuum, what we had is a wave equation, really exactly the same as general relativity. But remember that this h bar quantity has now a contribution from the scalar quantity. So we expect two tensor modes, as in general relativity, and a scalar one, which will be a breathing one. So looking into the trace of the field equations, we have this expression over here, which can be further simplified if we note that if we differentiate the effective potential, we get this relation between the derivative of the potential and the Ricci scalar, so that we can put it, plug it in here and get rid of the Ricci scalar, such that we have an equation for the scalar field itself. In particular, we have these equations, and we now perturb it, right? We have perturbed the metric field equations, and now we perturb the trace of those field equations, and we get a wave equation for that scalar quantity that I have introduced before. Remember, this is the excitation of the scalar field over the value that it takes in the constant background, right? So this introduces a mass term again, and we have simplified V naught to be 0, so to really understand what's happening. And this wave equation introduces a expresses a longitudinal scalar mode. So you see, we have counted so far 2 tensor modes, one breathing one in the wave equation of the tensor modes, and the longitudinal one with from the mass of the trace of the field equations. Okay, so we have found 4 polarization modes. However, there are claims that in FoF theories we can find some extra modes, namely vector modes. Okay, but at least from this approach, we have only found 4 polarization modes: 2 tensor ones and 2 scalar ones, which was in the spirit of what we have found previously, right? In the specific case of FoF theories. So this concludes the so-called metric approach to these theories. Okay, the metric approach, in the sense that the connection of general relativity is related to the metric field by the Christoffel symbols, or we can call it the Levi-Civita connection, right? But we can look into the so-called Palatini Formalism. And it is interesting to note that it was not Palatini who derived this formalism. It was actually Einstein in his first papers on general relativity that introduced this approach to general relativity. So the confusion that was made throughout history concerns a similar equation, but in a different context, that was found by Palatini. And since they had some resemblance, people had made this mistake. And so far, we can look into any literature on any gravity theory, and the literature will point towards the Palatini approach. But it's interesting to have this historical viewpoint in mind. So, in this formalism, both metric and connection are independent to each other. Actually, they are mathematically independent quantities. But in general relativity, we know that if we vary the action with respect to the metric, and the connection is given from the in terms of the metric, we get the Einstein field equations. And if we assume that the connection is not Levi-Civita, what we end up is by a constraint that so we vary the action relative to the metric, we get some equations, and we vary the action relatively to the connection, we get a constraint, actually a equation that implies that the connection is Levi-Civita. So in general relativity, both metric and Palatini approaches, or formalisms, as we want to express, lead to the same physical theory. So it's the same theory, it's Einstein theory. However, in other gravity theories, this is no longer the case. And let's look into FoF theories, as they are the simplest generalization of general relativity. So, for we vary the action relatively to the metric, we get this. Remember that the symmetrization arises because we do not know which connection it is. It could be not symmetric, for instance, if we included torsion, right? And we vary the action relatively to the connection, and we get this. The trace of the field equations here is a constraint equation, right? It's not dynamical. So that we will see what are the main implications of that. But to express, let's say, here I have R. Let's call it a calligraphic R, the curvature tensor that is expressed from a general connection. It's related to the Ricci tensor, which is expressed in terms of the metric field by these extra terms over here. So the Ricci, the scalar curvature is the Ricci scalar plus some further terms. Okay, this is interesting because these are tensor curvature. This is a scalar curvature, and usually they are the same as the Ricci tensor and the Ricci scalar, but as we have seen in general in FoF theories, they have extra terms which so to relate to each other. So remember that this is a constraint equation, and no massive scalar mode appears from here. It's not dynamic, it does not have a mass term, and it does not have a mass term. So the trace for a given function f yields an algebraic equation for R, the calligraphic one. So from this, we get that R will be a constant. If we insert back into the metric field equations, we will obtain f prime R minus times this quantity over here. So, which for this first term to be non-vanishing, this implies that this term here has to vanish, right? Let's do an example, because I don't know if you remember general relativity with the cosmological constant. Let's do this example, this exercise, right? So this is an exercise that I would hope you to do in 5 minutes, for instance, okay, to rewrite the Einstein field equations in vacuum with a cosmological constant by resorting to the trace of them. So remember, you cast the Einstein field equations, you take the trace in the presence of a cosmological term, you use the trace of this the trace equation, and you plug it into the metric field equation, and you will get something. Let's see, what do you get? Remember that these are the Einstein field equations in the presence of a cosmological constant. Please do the exercise or think about it. It's really simple. I would advise you to do it. It really helps to get sensibility, to get insight on this. I don't know if anyone has said something in the chat. I heard something. Okay, thank you. So I will change back to the presentation so to get so you can solve the exercise. I will give 2 more minutes. I think it's a quite simple exercise, but it gives a lot of insight of what's happening in FoF theories, for instance. Actually, this exercise also gives some insights on further analysis on different approaches of gravity, not here actually in gravitational waves, but in different things when we resort to this kind of it's a kind of specific tensor r mu nu minus what we will find, right? I won't spoil the exercise. All right. I hope you have finished your exercise. It was, I hope it was simple. It was just to get the insight. So let's solve it. So the idea is to take the trace of these equations, and we will get this expression here, right? So it becomes r, it becomes minus 2r, so it's minus r, and this becomes r over 2, so it's 4 lambda with a sign plus. So we substitute lambda over here, and we get r mu nu minus r over 4 g mu nu equals to 0. So this is precisely what we got in FoF theories in the Palatini approach, right? So that means that FoF theories in the Palatini approach are equivalent, in what concerns at least gravitational waves and the degrees of freedom, equivalent to general relativity with a cosmological constant. Okay, so only 2 polarization modes, the tensor ones, exist. Okay, this clearly contrasts with the metric formalism. So the same formal equivalent action, functional, leads to 2 different theories. You see, FoF theories in the metric approach are different from the FoF theories in the Palatini approach. Okay, so are the polarization modes and the gravitational wave solutions. So this is important. I think this was an important fact, so you get this insight that whether we are looking into the metric approach or in the Palatini, or even in the metric affine Palatini, the metric affine approach, where the metric fields also feel a different connection that is not related to the metric field. These approaches lead to different theories. Okay. So, and what about gravitational waves in the presence of matter fields in general? Remember what we had in general relativity and the other theories where only the gravitational sector is modified. What we do is we look into the homogeneous part, or at least the solutions in vacuum, and we extend this analysis by resorting to the green functions method. However, there are other approaches, just to get some insight. There's the so-called Campbell-Morgan formalism of general relativity, which also finds two polarization modes. There's the semi-classical theory of electromagnetic response analog. Okay, we get a modified dispersion relation. When the matter fields are magnetized plasmas, what we see is a cyclotron damping under Faraday rotation of the gravitational waves. And if we introduce a cosmological constant, the field equations lose their residual gauge freedom. Okay? So these are, when we introduce matter fields or a cosmological constant, which could be seen, for instance, in general relativity in a sort of equivalent way, either it's a kind of integration constant, or if it's arises from the energy momentum tensor. But if we introduce a cosmological constant, we lose the residual gauge freedom. Okay, let us further generalize FoF theories, and this this example is a work that I have done with collaborators in what concerns the gravitational wave solutions. This model was proposed by Bertolami et al. In 2007. So the idea is to generalize FoF theories by including a non-minimal coupling with the matter Lagrangian. So there is this non-minimal matter curvature coupling by the introduction of an arbitrary function of the scalar curvature, which could be different from this independent function here. So if we vary the action relative to the metric, we get these much complicated field equations, and we have, for simplicity, introduced this differential operator here. However, general relativity can be seen as the limit when f1 of r is equals to r and f2 is equals to 1. Using the Bianchi identities, we find that in these theories, the energy momentum tensor is covariantly non-conserved. So there is no longer a conservation law, in particular for matter fields. And in particular, a perfect fluid will feel a deviation from the geodesic motion due to the introduction of an extra force, which clearly depends on the matter Lagrangian choice. Let's suppose that the matter Lagrangian choice for a perfect fluid was minus rho. That will give minus rho minus p. However, if the matter Lagrangian density was p, which in general relativity is these formulations are equivalent for perfect fluids, this term vanishes. So these in these theories, the on-shell description of perfect fluids are no longer equivalent. Okay. So the idea now here of our work was to address gravitational waves in these kind of theories. So one way to do it is to linearize the field equations around the Minkowski background. And we have assumed, for simplicity, at least to grasp some physics of it, to, at first order at least, the matter Lagrangian is constant. Okay? By doing that, we find two excitation modes. Okay, two excitation modes, and these fluctuations can be expressed as fundamental fluctuations of the Ricci scalar and from the matter sector. You see here. So for let's analyze specific cases. One of them is the cosmological constant case. Let's assume that the gravitational wave propagates across a medium that behaves roughly as a cosmological constant. The wave equation has a mass term right here, but also remember the trace reverse or that we expressed in general relativity, right? Now we have a 1/4 factor here instead of 1/2. And this is due to the so-called lambda gauge that we introduce. We resort to this so-called lambda gauge, which was used in the work of Vastecker when looking into the role of a cosmological constant in general relativity. So we used this lambda gauge, and this yields a solution of the form. So you have the tensor polarization, we have the amplitude, and we have the propagation of a nearly plane wave. So the dispersion relation, so it arises, remember, the dispersion relation arises from the kk, the contraction, the contraction of k with k itself. So we get this term, which is precisely the mass term. But looking into the trace of the field equations, we get a propagating scalar mode, which will be the longitudinal one, right? Remember? So here, this polarization mode is a breathing one, which can be absorbed. But this one is a propagating scalar mode, which is precisely the longitudinal one. And in fact, it's this quantity, capital omega, is related with the excitation of the Ricci scalar. So this paper was quite interesting, as when we were writing down and we have submitted to the journal, there were no data on gravitational waves. But while the referee was reading and assessing our paper, the first results on gravitational waves and on the speed of gravitational waves appeared. So it was quite interesting to get the response of the referee asking for further analysis on this recent data, right? It was quite interesting. In particular, the so-called speed of the gravitational wave, which arises from this parameterization, okay, is constrained from these gravitational waves that were detected to be to lie in this range, okay? And for this series, our model predicted exactly one, so it's perfectly inside of this range. As for the group velocity, which was highly constrained by data, this was highly constrained. It was to be really close to the speed of light. These theories predict a value really close by small values to the speed of light in units. These are units of speed of light being 1, okay? So this was quite interesting to see that this model passed the recent at that time the recent constraints on gravitational waves. A next stage of this analysis is to consider a slightly different scenario. So now we do not have a cosmological constant case, but rather we have a dark energy fluid case, so that we can have some excitations on the matter field. Okay, so again, the procedure is the same. So we look for linearized. We look into this wave equation. When we used the so-called lambda gauge, and we have a solution of this form. But now we have a different dependence on the dispersion relation. And in fact, two scalar modes can be decoupled from the trace of the field equations. One of them, which is related to excitation of the curvature, and the other to the excitation of the matter field. So these these can be decoupled, but in general can have mixing. There can exist some mixing between the curvature and the matter, precisely because of these F2 terms. Okay, these introduce a highly non-trivial solution. It's really hard to find solutions except from the situations when we can really decouple the perturbations or the excitations of the curvature from the matter sector at the linear level. You are looking into the mixing has a second correction, a second order correction, okay? We can also address the Newman-Penrose formalism for such theories, right? Let's do like the way of doing by Alves et al. And look into this F1 of our function. But as for F2, we can also parameterize a deviation from the standard general relativity by these with general this term that depends on the Ricci scalar with a general index. So the trace of the field equations yield this solution, and we can look for specific solutions. Remember that choosing minus beta to equals to 2 means that this is roughly Starobinsky. Actually, it will be a plus, so you can include Starobinsky, so predicts a half minus alpha. Okay, it's the same, it's equivalent. But we also look into n equals 2 solutions, okay, in this coupling, non-minimal coupling function. So if we had some homogeneous and static scalar curvatures, of course, the scalar curvature does not have dynamics and will be 0. But for other situations, we have a more evolved solution or equation, actually, whose solutions are of this form. Okay, we have chosen the propagation of the gravitational wave to be on the z direction, and it evolves with time. So the dispersion relation will be modified, right, with this term. And we can now plug these solutions for the Ricci scalar into the metric field equations and look for solutions of the Ricci tensor. And here they are. So the non-vanishing Ricci, the components of the Ricci tensor are displayed here, so that the Newman-Penrose Ricci quantities here can be immediately found. Okay, you see, you have phi 2 like this, which is non-vanishing, which corresponds to a breathing mode. You have a phi 1, which is given in terms of the scalar curvature, and you have also the phi 0 or phi 0 to have this expression here. Okay, so let us think on this. Do you have new non-vanishing Newman-Penrose Ricci quantities? Are they in contradiction with Early's classification, right? We do not only have phi 2, but we have phi 1 and phi 0, for instance. Okay, are they in conflict? Would they be in conflict? Well, this is quite important, right? You could see, naively think this as a contradiction. Actually, it's not, right? So, firstly, for an exact plane wave, so this term will be roughly 0, right? Or nearly, it will be quite similar to 0. The phi 2 is related to the breathing mode, but this is related to psi 2. Remember, even in the Early's classification. So remember, the idea is to have those 4 Newman-Penrose quantities non-vanishing but linearly independent, so that there could be others that are non-vanishing but are linearly dependent. Okay, this is the case. Okay, So in any theory, if you compute and you find some non-vanishing Newman-Penrose quantities, what you need to be careful is, are they linear combinations of other ones? Okay, look it. Are they? Perfect. So in fact, for any metric gravity theory, it was shown by Erdely et al. And for nearly plane waves in the weak field, you have up to 6 polarization modes. This is the main message to take home. Okay, so you need to be careful. What you are looking at is to non-vanishing and linear independent quantities. Okay. And you can also look into other things like the gauge that you are using or the conditions that you have for the wave number, right? For the dispersion relation, okay, for instance. So you need to take all these into account and really find that these lies in some specific classification theory that you have the scheme, you look into it, and you see which polarization modes exist and what your theory really states of the further polarization modes in comparison to general relativity, for instance. Okay, so this workshop is finished now. So thank you very much for your attention. You have my 2 emails from the research center where I belong and from my university. And you can also look into my personal page on this ResearchGate network, where we usually put papers on this, like a kind of archive, right? So thank you very much for your attention. And please, if you have any question, please go forward and ask.
Thank you, Cláudio. Was really interesting, actually. I really enjoyed it. Thank you.
Okay, I'm glad you enjoyed.
Yeah.
I will give the slides of this second session. I will put in the Discord as I've done with the first session. So, but if you